Welcome once more. So now we also didn't forget to record it. It's great. Still people are joining, so I'll try to be a little bit slow in my introductions. So every edition of the COMSOC video seminar is special, but maybe this one is particularly special. We're having a so-called Rump Session, which means that we're going to have 10 people who have volunteered to each give a talk of 5 minutes. So overall, it should take more or less as much time as it usually does. It looks great, the program. I'm very much looking forward to it. We're going to do things in a similar way as usual. So people will give their talk. If you have a question, and maybe, hopefully, some of you will already think of a question while people are talking, please type it into the chat. And to distinguish it from other comments like people greeting each other and things like this, which is also a very good thing. If you do that, you do it like this. You type uppercase question followed by your question. It would be a bit easier for the speaker afterwards to find the things that they may want to respond to. And at the end of each talk, we'll have 1 minute for questions. Hopefully there will already be a few questions in the chat, and the speaker will just go there, look at those questions and decide what they want to respond to. On top of this, if you want to, you can also do the usual thing of raising your hand, your little blue hand that you can find in the windows. Click on participants. In the lower left-hand corner of this, you will see this blue hand symbol. And with this, you can indicate that you would like to ask it. I think I just got kicked out for a moment. I think it was probably my internet. I hope it's not going to happen too many times again. Anyway, once you're up and running and giving your talks, you don't really need me anymore. So we should be all right. Okay, I think we can start. So I would like Piotr, the first speaker, would like to ask him to share his screen and unmute himself. Piotr Skowron, our first speaker, is from the University of Warsaw. And once his thing is up, I will start the counter.
Okay, okay, thank you very much. So I'm going to talk about one specific concept from our recent work with Dominic. And hopefully this concept raises some open questions and might spur some follow-up works. We are in the model of approval-based multi-mineral elections. We are given a set of candidates, a set of voters, and the voters approve, each voter approves a subset of candidates. For instance, here, voter V1 approves 4 candidates, that is green lady, the red guy, the orange guy, and the purple lady. A voting rule takes such an approval-based preferences as input, takes a desired committee size, which in my slides I'll be always denoting by K, and returns a K element subset of the set of candidates. So here in this example, K equals 2. And I will use the following graphical representation of approval-based preferences, where the candidates correspond to the boxes, and each candidate is approved by all the voters that are below the corresponding box. So here we have 2 profiles, the left one and the right one, and these are the same profiles, but we're using different representations. Now I'll be using this graphical representation with boxes. So one concept that is related to proportionality and to stability is the core. So the idea of the core is the following. So let's say that we have a committee W at hand, and we say the group of voters S can deviate by proposing a subset of candidates T if the following 2 conditions are satisfied. The first condition says that they cannot propose too many candidates. That is the proportion that is, for instance, if the size of the group of the voters is 30% of the whole population of the voters, then they can propose only at most 30% of committee members. And the second condition says that each voter, in order to be able to deviate, must strictly prefer the candidates, the set of candidates that they propose to the committee that they deviate from. And this means that each candidate, each voter in a group S must approve strictly more candidates in T than in W. And we say that the committee is in the core if no group of voters can deviate by proposing any set of candidates T. So this is an example. Here we have 6 voters and the size of the committee equals 12. And the shaded committee is not in the core because we can see that these 3 voters, they form half of the society and they can propose 6 candidates, which is half of the committee members, so that each voter is strictly more satisfied with the proposed set than with the original committee. So there's an interesting open question. Does there always exist a committee that is in the core? No one knows whether this is true or not for approval-based preferences. So people try to look at different relaxed versions of the core. Usually the focus was on the relaxation by randomization or by approximation. And we proposed a little different kind of relaxation of this notion. And the relaxation that we proposed allows to view, for instance, the known property of extended justified representation, EGR, as a restricted variant of core. So let me explain this definition in our language. So for instance, here we have once again a group of 6 voters and a committee. And we can see that this committee once again is not in the core because these 3 voters can propose some candidates such that each voter is more satisfied with the proposed candidates than with the original committee. But here we can also see that the set that they propose has a specific structure, that is all the voters in the group S agree on all candidates in T. And we specifically want to prohibit this kind of deviations because they are the most harmful, the most likely to happen because the voters, it is easy for them to coordinate and to agree on the set that they want to deviate towards. Okay, so we try to, in our work, we generalize this concept by proposing the concept of core with restricted deviations. So we say that the committee W is, that given this committee, group of voters S can deviate by proposing a subset of candidates T subject to property P if the following 3 conditions are satisfied. The first 2 conditions are the conditions of the core, and the third condition says that the set of candidates they want to deviate towards needs to satisfy a certain fairness property P. For instance, in EGR can be viewed as a core with restricted deviations, where the property is a kind of unanimity property, which says that T satisfies this property if all voters in S approve T. Okay, and I'm moving to the open questions. So the open question is: can we find interesting properties P such that the core subject to P always is always non-empty? And also, does there exist a committee subject which is always in the core for restricted domains of preferences? Okay, sorry for extending my time a little bit.
Thank you very much. Let's unmute ourselves to clap. And then let's mute ourselves again, so it doesn't end in chaos. And then, Piotr, we have 1 question there, so you can start with that one. And if in the meantime other people have more questions, please do ask.
Okay.
It's a long question.
Okay, yeah, it is, yeah, so the question is why the group of voters would like to deviate only towards a set of candidates that is at most in the proportion of the size of the group of the voters. So basically the idea is that it is not the condition that they, which specifies why they would like to deviate, but this is the condition which specifies why they are allowed to deviate. In a way that it is, we would like to, the idea is that the group of the voters should be able to control the number of the seats in the committee, which is proportional to the size of these groups. For instance, 30% of the voters should be able to control 30% of committee members, And this is why we are only concerned with this kind of deviations, because they are in some sense fair, in some sense proportional. Okay, another question I see. Can I give my thoughts whether the core always exists? I have absolutely no idea. I tried to tackle this problem for quite some time, and I think it's like a very hard question. It's just technically very, very challenging.
Pick one more question that you can answer quickly.
And link with Nakamura theorem for the existence of the core. Actually, I do not know this one, this theorem. I know that there are some general theorems which says about whether the core exists or not. I think I'm not aware whether one can use them. But specifically about the Nakamura theorem, I cannot make a specific claim because I do not know this one. Okay.
Thank you very much.
Thank you.
Paul, you can already share your screen. So our next speaker is Paul Gölz from Carnegie Mellon University, and I believe he's ready to start talking. Go ahead.
Hi, this talk is called I Do Research on Sortition and So Should You. And I would like to start with something that Dominic said in his award lecture last week that's kind of resonated with me. He said that as voting theorists, the most obvious application of our work would be political elections. But because they're notoriously difficult to change, we should really be looking for places where there's growth in democracy. And I think that sortition is one of these places. And so I would like to speak about this. I would like to say some things about what sortition is and why it is exciting, then what we have been doing in this space, and finally, maybe an idea for what could be next. So sortition is a way of doing representative democracy. But the representatives are not elected. They're just chosen randomly from the population. Think about it as selecting K people without replacement from the population, which has nice properties on the political side of view, from the political point of view, which I'm happy to discuss offline. I'm very excited about it for these reasons, but it also has very nice formal guarantees, such as every person will be selected with an equal probability of K over M, and every group in the population that makes up for X% of the population will also in expectation make up for X% of the committee. And by concentration, probably even X post will be pretty close to that. So that is pretty cool. The other point why I think it's very exciting is that sortition really has been taking off in practice. There are more and more of these panels, and they now often are on a national level and sanctioned by the nation states. And furthermore, these NGOs that we've been talking to, they were very welcoming of collaborating with computer scientists. Some of them had been looking for computer scientists who could tell them about where their algorithms were fair and so on in the past, and we're very excited when we reached out. And some of our algorithms are now actually being used. So I think this is some of the reasons why I think doing research in sortition is very exciting. Maybe just as an idea of what kind of work we've been doing there, let me talk about some projects that I've been involved in. They were all centered around the question of how do we sample these committees. The first project dealt with the question of that maybe the sampling without replacement is not ideal. Maybe there are variants of stratified sampling that allow us to retain the same expectation guarantees for all groups, while also bringing down the variance in the number of committee members of certain groups that we care more about to make it more likely that these groups will be represented fairly. And then there's a whole other chain of research projects that Bailey Flanagan is also involved in, who is on the call, where we deal with the complication that in practice you can't actually sample everybody. People have to opt into this process. And the self-selection bias is more pronounced in certain groups in the population than in others. And so the challenge now is to build committees that are representative of the demographic makeup of the population as a whole, while still giving guarantees to individuals. And these guarantees could either be for everybody in the population or for people in a pool of voluntaries, where we see giving out the selection probability as a fair division problem. And we use the axiomatic method to try to decide how to select people very fairly. So maybe those just as a quick sample of things that we've been doing there. And what could be next? I think the main limitation of the approaches we've taken so far is that we look at sampling always in isolation. We just go to the point where the committees are formed and we say, well, vaguely, this committee being more representative more of the time is probably a good thing. But sortition really only starts there. They have outside experts that inform the participants. They then deliberate, and finally, maybe at some point, they vote. I think there's a bit of literature related to the question of how should you vote if you actually only have a representative sample of the population vote, and maybe which voting rules would be good for that. But I think that really looking at these steps in between of information and deliberation would be very, very valuable. Also because it's really not obvious how you should organize them in practice. For example, deliberation right now often proceeds in small groups first, where people internally discuss and then come together and discuss in a larger group. And looking at all of this together, I think would be very exciting. I, for example, have seen that Edith and Nimrod have recently written something on deliberation, and bringing this together with sortition and with this idea that the members of the committee are only a stand-in for the population as a whole, and that we would like the outcome of this deliberation to somehow mirror what a perfect society that would be able to just deliberate among all the millions of us at the same time, what the deliberation outcome there could be. I think that would be a super interesting discussion, and seeing what we can guarantee there would be very fruitful. So this is why I would love more computational social choice researchers to think about sortition, and I would be super happy to take questions, and please reach out to me if you're interested.
Thank you very much. So you can unmute yourself to clap. And thank you. I hope, so the first few entries there, they were still follow-up of the previous talk. I hope that some people are busy typing and will enter a question very soon. See, yes, now we have a question. Paul, you can start responding.
A single reference I think is somewhat difficult. There's a book that I really like by David Van Raybroek, which is called Against Elections, that I think is just a very nice to read political science and political point of view, which was what originally dragged me into this whole area. Otherwise, maybe just looking into the EC19 paper that we wrote about sortition is maybe a good idea, because we try to also just lay out the concept and why we're excited about that in the introduction. And maybe that can be useful. Otherwise, just reach out to me, please.
Peter, are you about to ask a question?
Yes.
Because you're unmuted? Okay, please go ahead.
Oh, sorry, I was typing. I'm bothered if a constant fraction of the overall population is completely unsuited to be elected, as I believe is the case. Then with sortition, you still will be electing those people.
Yes, yes, this is true, and I think it's very natural to have some reservations to this idea that just random people should make these decisions. But I find it very encouraging to just see the experiments that political scientists have been running, where the outcomes seemed super well reasoned, and I think these deliberations were, at least from the experience that we have, often steered in very productive directions, where at the end.
Isn't that just because you are operating in the experiments in a situation where the fools simply are not present, because you are starting with a restricted population?
That is, I mean, that is possible to some extent, that you have some self-selection that works in your favor there. But I think I have hope that it could even work with a real true sample, representative sample of the population.
Okay. Stanislav, can you already share your screen? And Paul, if you want, you can still respond to the one question in the chat while he's doing that.
Because random people usually don't know about the policy, they're experts from the outside, from special interest groups, academics, who try to just bring the information in the room and make a difference between just direct democracy, where you ask people point blank about their opinion about Brexit, and an informed panel where people have had the time to see all the points of view. And so you just try to bring all this expertise into the room. But the question is, how do you select which experts to show? And if many experts want to show up, how do you select the right ones? How do you bring them into the deliberation process? And I think there are no good answers there, even from the practitioner side.
All right, thank you very much. Okay, our next speaker is Stanislav Zhydkov from the University of Warwick. Please go ahead.
Hello everyone, I'm Stanislav Zhydkov, and I want to present some of the recent work we've done with Nicolas Mate and Paolo Turini on developing a new peer selection algorithm. The paper will be available in HK20 proceedings, but for now it's on archive for free to access. So in the peer selection setting, we have n agents that each review m other agents, and we also ensure that everyone is reviewed by m agents. And the overall aim is to select the best, the most deserving k individuals. So these assignments are drawn at random without predefined partitions, which is in contrast to some of the literature. Some of the prominent algorithms do rely on clustering and partition. And we do assume that there is a ground truth, which is represented by a linear order over the agents, which represents some kind of objective quality. Agents themselves don't have direct access to the ground truth. However, they do access some noisy observations using Mallow's model of the ground truth. So the problem here is that the agents may strategize to be selected to be in the top k. And we want to prevent that. And the big focus in the field is on developing impartial peer selection algorithms that do exactly that. So let's turn to our new proposed algorithm, peer nomination. The intuition is simple. So if you want to select k out of n individuals, we expect k over n proportion of each small review pool of size m to be accepted too. This way, we define the nomination quota to be k over n times m, and then we say that each reviewer nominates this many individuals. Obviously, k over n times m is not likely to be an integer, so the way we deal with this is we round the nomination quota down, and we say we let each reviewer nominate this many agents for certain, and then we let them nominate another agent with fractional probability, which equals to the fractional part of the nomination quota. Then we simply consider each agent independently and select them only if they're nominated by the big majority of their reviewers. So onto the properties of the algorithm, it's trivially impartial since the reviews of the agents have no bearing on their chances of selection. And it's also monotonic in the sense that getting a better review can only improve your chances of selection. The main downside, obviously, is that this algorithm is not exact, which means that it's not guaranteed to return k individuals every time. However, it is quite simple, which allows us to derive exact analytic expressions for the probability of selection for each individual, and hence then to derive the expressions for the expected accepting size and expected accuracy, so we can keep these things under control. Onto the empirical comparisons, we compared our algorithm against using the same testing procedure as Aziz and Ronald 2019 when they introduced the EDP algorithm. So we compared it against vanilla, which is simply the border count selection procedure, and a selection of impartial peer selection algorithms, most prominently exact dollar partition, which is considered to be state-of-the-art algorithm right now in the literature. And we can see that in almost all the settings, our algorithm seems to outperform the other impartial algorithms and even approaches the performance of border, which is not impartial in some cases. The only case where we don't perform that well is when m equals 5, that is when we have low information setting. Also notice that our algorithm is inexact, hence its accuracy can be artificially inflated or deflated if it returns more or less than k individuals on average. So we devised a fair test where we run peer nomination on an instance first and then use the output size as the target k for exact dollar partition. This way, each time both algorithms output exactly the same number of individuals. And using this comparison, we get the same kind of results. Peer nomination seems to outperform exact dollar partition in all cases apart from small m. This does lead us to an interesting question in the field, which is how do we compare exact and non-exact algorithms in general? So in our paper, we did establish a connection to the classification problem in the machine learning literature, but there is definitely more work to be done in that respect. And also, our algorithm can be improved perhaps by considering what happens when the nomination quota is not an integer. As for the big and open questions in the field, I think it's interesting to see how can we force honest reporting to be the only equilibrium rather than just one of many, because right now impartial algorithms only discourage lying rather than encourage honest and competent reporting. Thank you for listening, and I'm happy to answer any questions if there are any.
Thank you very much. So he is happy to answer any questions, and there is one, so please go ahead.
So if by the objective function you mean what kind of metric we use to measure the performance of the algorithm, we simply used recall, which is basically we measured how many of the true top K individuals our algorithm actually outputs. Yeah, which is in respect to the ground truth. Yeah, so does that answer your question? Okay, thank you.
Are there more questions? And if you don't manage to type it in, you can also raise your hand and I will invite you to unmute yourself. Wait a few more seconds. Zoe, you can already share your screen maybe, and then there's still a question from Ariel. Yeah, please go ahead. Yeah.
Okay, so firstly, our analytic derivations are in the case of no noise. We can incorporate noise in that, but it just makes the impressions very noisy and very unpleasant. And in that case, the expected output size is K in the case where there is no noise, obviously, and if K and M parameters are large enough. If they're not in some specific cases, if K and M are small, then we sometimes have to compensate the nomination quota by extending it or shortening it a bit to achieve the desired expected size.
All right, thank you very much.
Thank you.
Okay, I'm about to introduce the next speaker, but Zoe, so right now we see also a lot of stuff around your slides, and now we don't see your slides anymore. So while Zoe is looking for this, so Zoe Terzopoulou is our next speaker from the University of Amsterdam.
You don't see it?
No, I saw it, but I saw a lot of stuff around it as well, which I think was not intended.
I'm sorry. No? The same?
The same, yeah.
Just go full screen.
Yeah.
Or Control L? Yeah, Control L didn't work before. Okay, now?
Oh, very good. Yes.
Okay.
All right. Please go ahead.
Then thank you. So I'm going to talk about iterative voting with partial preferences, and this is just something I have been thinking about recently. So when I say partial preferences, I mean transitive orders that are also anti-symmetric, or otherwise you can think of them as strict orders where incomparability is allowed, but we have no ties. So in our setting, we have a group of agents and we have a fixed voting rule. And starting from their truth profile, the agents change their preferences one by one in order to achieve a better outcome for themselves. And the main question I want to address is whether convergence results of the literature are affected if we consider partial preferences instead of the standard linear orders. So let's see an example that I have taken from Level-Rosenchen. So in their standard setting with linear orders, they show that the two-approval iterative process does not converge, and two-approval means that we give 1 point to an alternative if it appears in the first two positions of a linear order. And we also consider a deterministic tie-breaking order in this example, as I have pictured it here. So we have Alice and Bob. They start with these two preferences, and we see that the green house is actually going to be the winner because it receives 2 points according to the two-approval. Then Alice, though, prefers the yellow house to the green one, so she can change her preference into this new one. And now, because every house receives 1 point, the lexicographic tie-breaking rule will select the yellow house, which is better for Alice. The same can happen for Bob in the next round. So now he changes his preference, and the blue house that Bob prefers to the yellow one receives 2 points, so is the winner. It's better for Bob. However, this can continue. Alice now prefers the yellow house again to the blue, so she is better off by switching to her truthful preference. And now, because of the lexicographic tie-breaking order, we have the yellow house selected. And finally, Bob will also have an incentive to return to his original truthful preference. And of course, you can understand that this cycle will continue, so convergence is not guaranteed in this setting. But what happens if we allow the agents now to submit partial orders? Well, now we have to define the two approval voting rule first. And the definition I use is that the rule gives 1 point to an alternative if and only if this alternative has at most one other alternative above it. So we start from the same profile as before and with the same tie-breaking rule. So Alice, in the first step, because she sees the greenhouse being selected, she will basically want to reduce the points that this greenhouse receives, and will flip this preference between the blue and the greenhouse in order to manage having the yellow house selected. But what about Bob? Now Bob sees the yellow house selected, and what he wants to do is that he wants to increase the point of the blue house that he prefers to the yellow one. And he has two ways to do that because he's allowed to submit partial preferences. He can just flip the arrow between the green and the blue house, or he can omit this arrow. And in this case, both the green and the blue house will receive 1 point because they will have just at most one other alternative above it, namely the red house. And here, it's an important assumption that omitting is cheaper for the agents than flipping. This is just an assumption you can think about for yourselves. But if we take that to hold, then Bob will submit this partial preference, making the red house the winner with 2 points. Sorry, the green house with 2 points. And again, Alice, in this profile with the partial preference by Bob, we have the blue house receiving 2 points. And the final round will consist of a change by Alice, which will go back to her original preference, and then we will have finally the greenhouse, the winner, with 2 points. And the interesting part is now we stop. So neither Alice nor Bob have an incentive to change their preferences anymore. We have reached an equilibrium, and it's an especially nice equilibrium because the second preferred alternative is winning for both agents. So this is just an example to illustrate what new questions arise in this setting. We can
So I don't know whether is it me who's frozen, or is it Zoe who's frozen, or everyone? Only her.
Frozen.
Okay.
You are not frozen.
I'm not frozen. Okay, good, because usually it's me who's freezing. So okay, Zoe is frozen. Now it is she. Yeah, I don't know whether she's still here. Let me just check. I think she got kicked out of the system. So let's collect questions for her. There is one. And let's wait a few seconds, see if she can come back. Maybe some Amsterdammers can write to her. I can't write right now. See. Okay, what I will suggest that we do, we move on to the next speaker, and then if Zoe manages to come back, we'll do a question period for her after that. So Joe, could you share your slides?
Sure.
So our final speaker before this break is Joe Singleton from the University of Cardiff. Please go ahead.
Cool, thanks for having me. Hi everyone, I'm a PhD student at Cardiff Uni. I'm going to be talking about my joint work with Richard Booth on our axiomatic approach to truth discovery. So I'll start off by saying what I mean by truth discovery. It's a problem mainly been looked at in relation to data mining, crowdsourcing. And the idea is to find true information when given conflicting reports from multiple sources. And the core idea for doing this is to estimate the trustworthiness of sources at the same time. So the idea is we can try and handle cases where the sources of information vary in their reliability and we don't know who to trust ahead of time. So I'll illustrate the problem with an example. Suppose we have 4 sources of information here, S through to B. So these could be people or sensors or any kind of agent which provides information. We have 2 objects of interest. So objects represent the entities about which we're trying to find the truth. So these could be questions we're trying to find the answer to, or propositions which we want to determine whether they're true or false. Each object has a number of facts associated with it. So these represent the potential truths. Our assumption is that each object has one single truth associated with it, but of course we don't know ahead of time which one that is. And finally, the sources provide their information by making claims for a subset of these facts. So in this example, let's suppose source S here claims that F is the true fact for object O and that H is the true fact for object P. Let's suppose that T actually can disagree with S on both counts. So T claims the opposite fact for both objects. And finally, in this example, let's say U and V only comment on object P and they agree with T in this case. So this is an example of the kind of input we're dealing with. There's both agreement and disagreement between the different sources on a number of different issues. And so given this kind of input, the goal is to determine on the one hand which sources we should trust and on the other hand which facts we should believe. So in our work we view the output as 2 rankings, 2 total pre-orders. One of the sources, which will give the relative trustworthiness between different sources, and one ranking of the facts, which gives the relative believability, so how inclined we should be to believe that as the true fact. And so from these rankings, we can estimate the true information just by taking the maximally believable facts for each object. Okay, so given a graph of this form in general, there's of course lots of different methods for coming up with rankings. So our question has been to look at what makes a good ranking system, what kind of properties should we be going for. And so we've done this by viewing it as a social choice problem and taking the axiomatic approach. So you can probably see that it's already similar to some well-studied problems in social choice. You could view it as a form of voting, where the sources are voting for which facts they think are true. Of course, it's similar to judgment aggregation. You can see the sources giving their judgment across these different objects. And the main difference in this case is that whilst we want to treat the sources fairly in a way, we don't want to treat them equally per se. The idea is that some sources might be more or less reliable than others. And we should try and, to some extent, ignore the unreliable sources. So due to the similarity with these problems anyway, there are a lot of the kind of standard axioms that can be carried over and reformulated in our framework. So we have versions of anonymity for sources, neutrality for the facts and objects. There's ideas of positive responsiveness and monotonicity can play a role as well. So if we consider adding an extra edge going into a fact, corresponds to some extra support for that fact. So that should go up in the ranking of facts. Also ideas of independence as well can play a role. But the main important and interesting axiom to look at here is the thing that really characterizes truth discovery and differentiates it from these other problems. And that is, of course, the ranking of the sources, the trustworthiness, and in particular, the relation between these 2 rankings. So a common idea that's present in a lot of the truth discovery work is that a source should be seen as trustworthy if they provide believable facts. And on the other hand, a fact should be believable if it's backed up by trustworthy sources. So there's a kind of 2-way mutual dependence here between the 2 rankings, which can make it hard to think about what the best choice is in a situation. So I won't go into the details of our axiom, but it tries to get across that principle. And interestingly, combined with the more standard ones, it already rules out some kind of basic voting rules basic ranking methods you could think of. For example, if we just rank the facts by counting the number of claims. And so this has led to the first impossibility result for truth discovery. So I hope that gave an overview of how we looked at the problem. All the axioms and the full paper appeared as an extended abstract at AMAS this year, if anyone's interested. Thanks.
Thank you very much. Let's clap. And I think most of the things that were there in the chat were still organizational matters and a couple of late questions for Zoe. But now we have a first question for Joe. So you can go ahead and answer.
Oh yes, about correlation between sources. Yes, that's a very good point. So in our work so far, we've been more or less assuming that the sources make their claims independently. So that if you have the same thing from two sources, that kind of boosts the credibility of the thing they're saying. But as you mentioned, this is not really the case in the real world, because people do copy each other. So yes, this is definitely something that other people have looked at in the truth discovery area, and it's something we should also incorporate in our work. But I guess for simplicity in this first version, we've assumed independence between the different sources.
Okay, do we have any other? Yes, there's another one from Bill.
Oh, I see. So noise control was in
no, sorry, no. There's something. No, sorry. This is something else. This is organizational matter that you're not supposed to see. Some weird people waiting in the waiting room that we probably shouldn't let in. Okay. Are there more questions for Joe from anyone?
Mine was a question.
Yours was a question. Okay. Yes, please, Bill.
Have you considered noise models in which each agent initially draws a probability of being correct and then makes a noisy observation?
Yeah, it's a good point. I think a lot of the work in like the crowdsourcing point of view takes a similar point of view. There's you have kind of the true reliability levels are taken as a probability, and things like maximum likelihood estimation, expectation maximization is very common to do this kind of thing. So kind of get the most likely reliability levels given the data you see.
All right, thank you very much, Joe. Then I would like to ask Zoe to unmute herself briefly and see if she can answer to a couple of the questions that have popped up in the chat earlier.
Yes, okay.
You can see them. Yeah.
Yes, thanks for the screenshot of the chat. I think that was very useful. Okay, I'll go through the questions quickly. So is that method equivalent to approval voting with at least 2 alternatives approved on each ballot? No, well, at least 2 alternatives, not necessarily, because if the agents just submit a linear order, then they will approve a single alternative. Yes, so 2 alternatives for linear order, and then more for partial orders with incomparabilities. Okay, yes, so I see what you mean. Yes, I think that's correct. Yes. I have to think more specifically, but I think it is correct. So next question, can you give an intuitive scenario in which omitting is cheaper than flipping? So yeah, that would be context specific, but we were thinking of, for example, a website where you need to click in order to hide the preference that you have already submitted. And then once you have already omitted the preference, maybe click again to add the opposite one. So in this case, 2 clicks are more expensive than 1 click. So flipping would be more expensive than omitting. Then I think Ulle can just stop me whenever our time is over, because I'll just keep reading.
10 seconds.
Okay, then I'm going to go for the next one. Would it make sense? Oh no, that's not my question. Am I right in your second example, 2 approval rule gives 3 points? Yes, that's true. So 2 approval will maybe give more than 2 points if there are more than 1 alternatives that are not dominated by more than 1. So yes, this is maybe not a supernatural definition of 2 approval. But in this case, we couldn't think of a better one. So if you have any ideas, please feel free to tell me.
Okay, thank you very much. So we still have to clap for Zoe, so let's do that now.
Yeah. Thanks.
Okay, so what we're going to do now? Now we're going to have the coffee break. So we're going to set up these random breakout rooms. So Dominic will set it up, and it will happen in a few seconds. So if you want to, you can press yes. Okay, I'm entering the breakout room, and then you talk to these 5, 6, 7, 8 people that you will meet there for 10 minutes, and it will call you back. It might be that the screen goes blank for a few seconds, so don't worry about that and just go ahead with it. Or if you really need a break and don't want to see anyone for a few minutes, that's also, of course, completely fine. And I'll see you again in 10 minutes. So we still have to wait a few seconds for everyone to come back.
I think we should be ready.
I think we should be ready. Okay, great. So then welcome back, everyone. We have another 5 speakers, and the first of them is Aziz from the University of New South Wales in Sydney. Harris, go ahead.
Thanks, Ulle. Can everybody hear me?
Yes. Okay,
so what I'll present today is based on 2 pieces of very recent work. The first paper is by Rupert, Nisarg, and Rohit, which has been recently accepted at ACM EC 2020. And the second is a working paper of mine. So the setting that we are focusing on is one in which we have agents who have additive positive utilities over individual items. And we are interested in outputting a probability distribution over integral allocations. And the main challenge we want to look at is simultaneously achieving good fairness and efficiency properties, both ex ante and ex post. So here's a snapshot of some reasonable efficiency and fairness properties one may consider. Those of you who work on fair division, you might be familiar with EF1 or envy fairness up to 1 item. So we may want to consider deterministic outcomes which satisfy envy fairness up to 1 item, so EF1. We may also want to have a probability distribution which gives us ex ante envy fairness. Similarly, we also may want to satisfy combinations of nice efficiency properties such as ex ante Pareto optimality or ex post Pareto optimality. So if you consider any of these main notions, let's say ex ante envy fairness, there are well-known algorithms which can manage to find an ex ante envy free outcome. For example, competitive equilibrium with equal incomes or the probabilistic serial mechanism of Bogomolai-Moulin, they do the job. Similarly, if you want to focus on ex post EF1, there are very nice algorithms by Lipton et al. Or the maximum Nash welfare rule of Karyanis et al. From 2016 EC. In fact, this rule even gives you simultaneously ex post Pareto optimality as well. So what's interesting about this paper by Freeman et al. Is that they started looking at these combinations of properties, and they presented many nice results, but I'll mention 2 particularly relevant results. So the one result in green is an algorithm in which both the properties in green were satisfied by the algorithm by Freeman et al. And another nice result they've showed was this result in which these 3 properties in pink are not compatible simultaneously. So this is very interesting because ex post EF1, ex ante envy freeness, and ex ante Pareto optimality, they're very nice properties, but you simply cannot satisfy all of them at the same time. So I've done some more work on this problem, and I looked at what properties can be satisfied. So the first result I had in this space was an algorithm which satisfies these properties in green. I will not give you all these definitions. They're all variants of envy freeness and Pareto optimality, weaker and stronger versions. The reason I really like this algorithm is that it's a very simple algorithm which combines some very elegant established algorithms from the field, including network flows, probabilistic serial, Hoprovkov algorithm, as well, and also Birkhoff's decomposition algorithm. So this was one algorithmic result I had, and can we do something better? Well, it turns out that in some ways, this algorithm of mine satisfies a maximal set of properties. So I had a couple of further impossibility results, which are highlighted in these pink dotted rectangle or this solid pink rectangle as well. So this shows that these properties in pink, they are not, they cannot be satisfied simultaneously. So what's next? Well, we come back to this original question which Freeman and et al. Asked. So I've highlighted these three properties in yellow: ex post EF1, ex ante Endriss, and ex post pre to optimality. This is still an open question whether there is a nice algorithm which satisfies all these three properties simultaneously. So I just wanted to give you a snapshot of a couple of these papers. I haven't given you any definitions. If you have questions about clarification, I can answer them in the Q&A. And I'll conclude with a shameless plug on a book chapter of mine, which discusses many other similar issues around probabilistic allocation. So I thank you for your attention.
Thank you very much. So there's already one question and maybe half an answer to it, but you can still answer it yourself.
Unshare.
No, you can answer the question and you can unshare your screen, that as well. Yes, you can stop sharing your screen and you should have, you have a question.
So I'm looking at Bettina's question. My guess is that you have a probability distribution over EF1 allocations. Indeed.
So look at the one above. Yeah.
Okay. Yes, Bettina has a probability distribution over EF1 allocations. Hadi asks, what do you mean by SDEF1? So the understanding is that by removal of one item, you can achieve SD Endriss. So that's what I mean by SDEF1.
Okay, do we have more questions? You can also raise your hand if you want and ask it on the microphone. I'm going to ask Hadi already to please start sharing his screen while we're waiting whether there's still another question. There's one.
What about EFX? I haven't looked at EFX. People are still trying to figure out what about EFX even in the space of deterministic allocations.
All right. Thank you very much. Okay, then
Thank you.
Our next speaker is Hadi Hosseini from the Rochester Institute of Technology. I misspelled his name in the announcement, but it's all fine now.
Right.
So Hadi, please go ahead.
Thank you, Ulle. Hello, everyone. My name is Hadi Hosseini, and I'll be presenting my work on fair division of time or multi-layered cake cutting. This is a joint work with Ayumi Igarashi, who is now asleep. She told me that she cannot join because it's really too late for her, and also my student Andrew Stearns. So I'll start by motivating the problem and just give you a scenario that we probably have seen a lot for us when we are kind of trying to make decisions or make some sort of schedule for ourselves. So imagine that you want to kind of go to and use different types of facilities that are available in your college or your university. Obviously, this should be the time that there's no pandemic, but we are thinking about like normal times. So you want to use these multiple facilities. So you imagine there is a seminar room, there's exercise room, there's different types of rooms that are available, and you might have different preferences over what time of the day you want to work in these facilities or use these resources per se. So for instance, you might say, well, I would like to get up in the morning and exercise for 2 hours. And then in the evening, I would like to have like 4 hours of the seminar room and use the seminar room. Someone else might say, well, I would like to kind of use the seminar room in the morning for the full from 9 to 12 and like work on some like brain power with my friends. And then maybe in the evening when I'm tired, like thinking and solving problems, I'll just go to the exercise room and I would like to use the exercise room. So this type of problems becomes more nuanced because different people might have different types of valuations or different types of needs, or as we say, preferences over the time of the day that they would like to use different resources. So in this case, for instance, we can assign Alice. Alice can use the seminar room in the morning and then use the exercise room in the afternoon, and Bob is going to use the other complementary times. Now, the question that really comes into play is that how do we fairly allocate different time intervals? So this is essentially, as most of you know, kind of reminds you of the cake cutting problems, right? So how do we fairly divide a cake or a divisible resource among agents with different valuations or different preferences over time, right? So it's a very standard time, and we're familiar with many of these type of problems here. So one approach would be that you might say, well, let's start by just treating each of those resources independently, right? So we have tons of protocols depending on the number of agents and depending on what properties we want to satisfy or what type of fairness notion we want to satisfy. We can use, we can just make fair allocation for each of those resources. The problem is that this type of approach might work, but it might not, it might give us like some sort of problems in sense of scheduling. So for instance, we might assign, we might assign overlapping intervals to the same agents, right? And the agent who is kind of assigned to work in the seminar room and at the same time to work in the exercise room, that agent may not be able to benefit from all the time. So because there's going to be an overlapping time between them. And by the way, so something that I'm not sure if I mentioned is that we are assuming that each person is going to use, each resource is going to be used by only one agent, right? So it's the resource itself at each time step. So other than the problem of overlapping preferences, the overlapping solutions, we might have problems with the solutions might be fair for each of the resource, but may not be fair overall if we consider all of the resources that are out there. So this is actually initiates our work. This kind of motivated us to study this this type of problems that which we're going to call them multi-layered cake cutting. So we are assuming each layer each resource is a layer, and we are going to cut this resource in a way that agents get feasible solutions, right? Feasible and fair solutions. Now we're going to look at these type of problems with two conditions. These are the main conditions that we're looking at. The first main condition is feasibility. We want each agent to get non-overlapping pieces, and also contiguity, which means that we want each agent to get one piece. You don't want an agent to have half an hour in the morning to go to the seminar room and then 3 hours in the afternoon. We want this to be all connected. So the natural question is that what fairness guarantees can be achieved under these constraints. So you're more familiar with the envy freeness notions and proportionality notions. I'm not going to go through that. It turns out that we can get envy freeness by some modification to the cut and choose protocol, where we can kind of do some sort of diagonal cuts, right? And with these diagonal cuts, we can satisfy the envy freeness for 2 agents and 2 layers. When it comes to 3 agents and 2 layers, then we're going to need the moving knife protocol. This is where we introduce new things, and we call it short knife and long knife, which I'm not going to go into the details. I just want to wrap it up by saying that we have some results for envy freeness and for proportionality, and these results are some of them existential about the existence of these. Some of these results work independently, and some of them work where we had to remove contiguity. So this contiguity and adding contiguity to the feasibility condition is actually creates a lot of open problems. And I just want to tell you that if you have any questions, reach out to me or Ayumi. We're happy to take any questions, or if you want to collaborate, we're open. If you have any thoughts or anything that you want to kind of share with us, we'll be happy, and we'll appreciate that. And thank you very much.
Thank you very much. Let's clap. All right. There's already a question in the chat, Hadi.
Yeah, so Nisarg is asking, have we considered the discrete version where we have like some hourly time slots? In fact, we started with that problem, and we realized that even the non-discrete version hasn't been solved. So that's actually in our current ongoing process, ongoing work that we're working on. We started with that question, and that was our actually main question. And then we realized that this part has not been solved. So we're solving this first. Yeah.
All right. Any other questions? Neil, you can already maybe share your screen, and then we're still waiting a few seconds if there's another question coming through. right. Okay, thank you very much. Then we're moving on to the next speaker, Neeldhara Misra from the Indian Institute of Technology at Gandhinagar. The floor is yours.
All right, thanks very much. Hello, everybody. So I would like to just talk about a cute open problem that I think I found. Hopefully it's not something simple that's just completely escaping me, based on something that we've been looking at recently. So we're going to be talking about the fair division of indivisible goods with potentially mixed valuations, and when we also allow agents to possibly share. So usually we encounter hardness statements which use phrases like, this problem is hard even when valuations are identical. Typically, this is because of some connection with a partition type problem. And one question we want to ask is, what if the narrative was not even when preferences are identical, but perhaps when only when preferences are identical? So that brings us to the question of how do we capture the identicalness of valuations? Well, one way to do this is using the so-called degeneracy concept, which is the largest number of items that are similarly valued by any pair of agents. And we say that items are similarly valued by a pair of agents if the ratios of their valuations are the same. So it's straightforward to check that the degeneracy of a profile that consists of identical valuations is as large as it can be, which is m-1, where m is the number of goods, whereas on the other extreme, the degeneracy could be as small as 0 when this happens when no pair of goods are valued in the same way by anybody. So it turns out that finding complete EF allocations continues to be hard, even for instances that have very low degeneracy, which would be the other end of the spectrum, where everything is non-identical. But if we insist on EF allocations, which are fractionally Pareto optimal, then we have an algorithm, and this is, by the way, work that came out last year on the archive by Feder Sandomierski and Edel Segel-Halvi. So the situation here is that if you look at the form of the running time, it's quite nice when the number of agents is fixed, but it kind of blows up if they're not. So the question that I'm wondering about is what happens if the number of agents is unbounded and the degeneracy is still small? Can we do better? And to this end, we have some observations. One is that if the number of agents is unbounded and the degeneracy is constant, we do get NP hardness. So we can show that it's NP hard for instances with a large number of agents with bounded degeneracy. But what is not clear is if the problem is fixed parameter tractable, as it were, in the combined parameter number of agents and degeneracy. So based on the results that are already floating around, we know that some combinations of running times are ruled out, and it's the possibilities that are shown here are ruled out just as consequences of the existing NP hardness results, but it's still not clear if we might get something. We may have an algorithm whose running time is of the form some exponential function of both D and N. As I say, it'd be great to know if I'm just missing something that's otherwise straightforward, but we thought it was interesting. So actually, I'm more or less done here. I just want to spend maybe 30 seconds talking about why I think instances with constant or low degeneracy are interesting. So unlike voting, where all preferences being the same is probably an indicator of high consensus because everyone feels the same way about a certain set of issues, in the resource allocation problems, it would seem as if having identical valuations is actually a situation with contention. So it seems like low degeneracy means that agents are friendly and they agree. The question is, can we do better here? So I'll call it a wrap with that.
Thank you very much. Perfectly in time, even faster.
Thank you.
But there was one question already in the chat. I hope maybe more will come. And I think Peter wants to ask one as well. So go ahead, Peter, you can. And now you're muted. Now you're
Sorry,
muted.
I didn't have a question.
Okay, that's unusual, but we can handle that, yes.
So I think there was a question about what sharing means. So this is simply the fact that when you're allocating the resources, they don't have to be, so typically you would give one item to one agent, but now you can distribute this item. So you basically allow for fractional entries in the allocation. And of course you want it to be normalized to one, etc. But in practice, this just means that maybe a resource can be time shared between agents, etc. I hope that answers the question.
Okay, any other questions? Yes, there's one coming.
No, so for binary valuations, this is actually tractable because once you insist on low degeneracy and binary, there are only so many distinct, so the whole instance is bounded as a function of the degeneracy and the number of distinct values. It's actually a small technical subtlety with binary valuations because of how zero entries are handled in the definition of degeneracy, but I can speak more to that offline. Yeah.
Oh, I meant binary encoding. So.
Oh dear, yeah. Okay, so yeah, that's a good point. So our NP hardness result is a strong hardness result. So all our valuations are polynomially bounded, but on the other hand, the other NP hardness results are not. So they're based on, again, partition type problems. So it's a good point.
Okay, cool, thanks.
Like one last question. There's a question of Hadi in the chat.
Right. So interestingly, our first hardness results actually worked with this version where we had precious codes that couldn't be shared and things like this. And we really viewed them as assumptions that we eventually got rid of. From the algorithmic side, this is a perfectly reasonable variation where you might have selfish agents and, you know, valuable codes that are just not up for sharing. And I have actually no idea. Sorry. So.
All right, thank you very much. Could you stop sharing your screen, and then if Ronald, as soon as it's free, you could share yours. So our next speaker is Ronald Haan from the University of Amsterdam. Ronald, go ahead.
Yes, thanks very much. Okay, so what I want to tell you about is some kind of research direction that I've been looking at, explain a little bit the idea. And I have this nice little problem that I still have open. So I'm open to suggestions, ideas, whatever. And also in general, I'd be happy to have input and feedback and comments on the general approach. Right. So what I want to do is I want to kind of study different representation languages for probabilistic preferences. So if you want to model uncertainty in preferences, one way to do this is to see this as a probability distribution over certain preference orders, either linear orders or partial orders or weak orders. You can play with this. And so what I want to do is, so what I've already been doing is studying and comparing different languages to represent these probability distributions. What a language is basically just a way of specifying some expression, and this expression has a semantics that is a probability distribution over linear orders, weak orders, etc., over some finite set of alternatives. And what I'm doing is I'm studying these languages to see how do they compare in terms of expressivity. Can I express everything in this order? Can I only express certain distributions? How do they compare in terms of succinctness? Do I need an exponentially large representation to spell out some distribution? And their support for different efficient operations, queries, and so on. So this is kind of like a knowledge representation approach to doing this. At the moment, I'm just looking at individual preferences. So I'm not kind of studying a multi-agent aggregation thing, but that's also something that I would like to do. So let's look at some examples also to get to my concrete open problem. So one way of specifying these probabilistic preferences is basically just spelling out a lottery over different linear orders. So in this case, for example, I have 25% probability over the order A1 over A2 over A3, a 50% one over this order, and so on. So all these things add up to 1, and I can basically sample from this and so on. So that's one way. Another way is to kind of start with utilities for different alternatives. So for example, in this case, I have alternative 1 has a base utility of 2, alternative 2 has a base utility of 4, alternative 3 has a base utility of 3. And then I have these little lotteries that add or subtract value. So for example, for this alternative 1, I have a 50% chance that actually it's worth 4 more than its base probability. So maybe there's some uncertainty over the quality or the state of some alternative. And if it turns out to be in a good state, then it's worth 6. And if it's not, then it's worth 2. And so similarly, I mean, you can just add positive or negative numbers. And so this also gives a linear, or this gives a probability distribution over weak orders. So in this case, I chose it in such a way that it always ends up being a linear order. So I have a probability distribution over linear orders. But it might turn out that 2 alternatives get the same utility, and then I would say, okay, they're equally good. And so now here is my my open problem. It seems quite simple, but I couldn't work it out. So the question is, can I express uniform distribution over, say, all 6 linear orders for 3 alternatives using this utility-based lottery? My feeling is no, it doesn't work, but I couldn't prove it. So I'd be very happy to, if people have ideas, or maybe it follows easily from some known result. So if you have ideas about this particular problem, or if you have ideas or suggestions for things in general, in particular, I would be happy to hear people's thoughts on what might be good representation languages that make sense in a social choice setting. That's it. So maybe I'm even short. Thanks very much.
Thank you very much. Okay, so questions. There's one already in the chat.
Yeah, so there's one thing that, so Peter asked, is there not a simple information theoretical lower bound on the size of expressions? Yes, so for this simple example, if I allow only one additional lottery per alternative, then I have 2 to the n possible orders, and there's n factorial many linear orders. So then it's not possible, but I could have multiple additional lotteries per alternative, and then I'm not sure if there's any trivial lower bound.
What I mean is that the more interesting case is to look for specific expression language which can concisely encode some class of preferential orders, but then may fail completely on different ones. And there various languages might differ.
Yes, yes. So I agree completely that in the general case, this is a very useful tool. And indeed, there are representation languages that are very good at, for example, expressing uniform distribution over all others, but not everything. So yes, indeed, I agree. Let's see. So Paulo has another question. How is this connected with the von Neumann-Morgenstern representation theorem? I don't know. Actually, I don't know about the theorem, so I should look it up, I think.
Do we have more questions? There's one more coming.
Okay, so Bill asked, what's wrong with drawing utilities uniformly from random from 0, 1? So the problem, I mean, so maybe it's a technical problem. The problem with that is that it might turn out that, I mean, there's a non-zero probability that two alternatives get the same utility, and then they're not.
It is a 0 probability, but it's not impossible.
I see. Okay, if you do, yes. Yeah, so then I guess it depends on how I represent the little lottery. But that's a nice suggestion. Thanks.
So Nick, can you already share your screen, and then Ronald can maybe pick up?
I'll look at
one
Nisarg's question.
Yeah.
Am I correct in understanding that Bayesian things? Yes. So Nisarg, the answer to your question is yes. It's basically equivalent to specifying a discrete distribution, although it might be more compact. So maybe I can have a compact representation for exponentially large thing. Yes. Thanks.
All right. Thank you very much. All right. Then for our final speaker of the day, Nick Arnosti from the Columbia Business School. Nick, please go ahead.
Thank you, Ulle. Okay, so today I'm going to be telling you very briefly about a new model of stable matching that I've developed. So the classic stable matching problem. So first question, why do we need a new model? We have an existing model of stable matching. It seems to work pretty well. And my assertion is that basically we don't currently have a very good understanding of how the inputs, say, to the deferred acceptance algorithm affect the outcomes at the end of the day. So in particular, there's a number of examples illustrating that small changes in, say, the number of participants on each side can have a big impact on final outcomes. So I'm just going to give one example of this that some of you may be familiar with, which is from a paper by Ashlagi, Kanoria, and Leshno. And so what they show is that in a matching market where the two sides are balanced, there's equal numbers of men and women, and preferences and priorities are drawn uniformly at random, adding even a single person to the market can dramatically shift outcomes. So here we have a graph reproduced from their, or just copied from their paper. So on the x-axis, we have the number of students. And on the y-axis, we have the average rank of what students receive when you run the student proposing deferred acceptance algorithm. And so you see this kind of very, very abrupt jump when you go from one fewer student in school to one more student in school. And this was one result that I think many people in the matching community found surprising. It's a very interesting result. Of course, it's very brittle in some senses, right? So it depends on complete lists and uniform random preferences. And if you, as soon as you try to modify, for example, the preference structure to add correlations or other things, it becomes very, very intractable to work in a finite model. And so one might think, well, let's work in a continuum model. And sure enough, people have thought about that, right? So one very nice continuum model is that by Eduardo Azevedo and Jacob Leshno. And essentially what they do is they try to predict a cutoff score. What does this mean? So basically, think of each student as having a priority at each school. Higher is better. And then the cutoff score gives the minimum priority that's required to get into that school. And so Azevedo and Leshno kind of try to predict what the cutoff score will be given market primitives. And here's a graph of simulation results from their paper. So each of these panels corresponds to a different size market as measured by number of schools. And then each x-axis corresponds to the size of the schools themselves. And so intuitively, if schools are very large, then the law of large numbers implies that the cutoff score should be predictable at each school. And so here we have the red lines give the 5th and 95th percentile of the realized cutoffs in a simulated market. The blue line gives the average cutoff score in their simulated market. And the black dashed line is their model's prediction. And so what we see is that when capacities are large, like each school has 200 seats, then the empirical cutoff distribution concentrates around their model prediction. But when seats are much smaller, there's actually a lot of stochasticity. And so it's not reasonable to kind of summarize cutoff scores with just a single number, right? So if my priority at a school is, say, 0.65, I actually have a chance of getting in, even though it's below their predicted cutoff. And we might want to be able to estimate that chance. So basically, I've developed a closely related continuum model, but this actually predicts a cutoff distribution at each school. And so a picture is worth 1,000 words. So I'll just show you what are the predicted distributions from my model. So I'm able to predict these percentiles for any given percentile. And as you can see, they match very closely. So in particular, we can also actually take my model and go back to the work of Ashlagi, Kanuri, and Leshno and say, okay, for this chart, what does my model predict the average rank should look like? And here's the model prediction. So empirically, and I have other graphs in the paper, but empirically, this model seems to make very good predictions. Furthermore, to a theorist like myself, one of the exciting things is that analytically, it's possible to use it to prove new theorems. So I'm really excited about this model. I think it offers a lot of flexibility while maintaining tractability. I'd be happy to answer your questions.
Thank you very much. Let's all unmute ourselves and clap. Good. And then please type in your questions or ask them through the microphone. That's also fine. There's one coming in.
Okay, when you ask about better solutions, what do you mean?
Yeah, so I don't have an idea. That's why I put it in a quote unquote. I just thought that you have an explanation of what a better solution is going to mean. In these type of problems, you care about the stability and you care about perhaps efficiency on one side.
Right, so the goal of this project is merely to stick with the standard traditional definition of stability, but to come up with a model that can predict outcomes in markets with non-trivial randomness. So you can imagine students have preferences and priorities drawn from random distributions, but maybe my preferences are correlated with my priorities. And so now I want to make a prediction about that and just understand what will happen in a stable outcome. So it's not so much about changing the algorithm as understanding the existing algorithms or definitions.
I see. Thank you. Thank you very much. Yeah, makes sense.
Bettina, you are unmuted on purpose. You want to ask a question? No. Okay, Bill has a question.
Okay.
In the chat.
Yeah, so I see a better outcome. Yeah, so I think one nice thing about this model is that because it makes the analysis of outcomes more tractable, I think it could potentially be used to analyze strategic incentives. For example, if I'm, choosing to only list a subset of schools, then maybe that hurts my outcome a little bit, but I save on cost. So of course I haven't actually tried writing out that model, but I think some sort of model where basically people are strategically choosing what to list has so far been pretty intractable. And I think with the help of this model, it might become more tractable.
All right, thank you very much. I think we should stop here. Could I ask you to stop sharing your screen for the final few minutes? So as always, we leave it on for a few more minutes, the session. If people want to mingle, if you still want to ask any of the 10 speakers a question, I think they're still here. You might still manage to reach them. The first few people who typed something into the chat now seem to be very happy with the Rump session. I was also very happy, also found it a bit exhausting, even more so than chairing a Rump session in the real world, but it's absolutely worth it. So I'm sure we're going to do this again in a few weeks' time. What I will do now is I will announce that next week we'll have a standard seminar with 2 speakers at the same time. Gabriel Demange and Yair Sik. Yair just sent us an email that he's going to speak about something different. So right now the website I think is not up to date, but it will be very soon. I will have a nap after this, and then I will update the abstract on the website, or maybe Dominic is faster than me, but he may also have to have a nap because for him it's still early in the morning. So, but it'll happen. So then I see most of you again next week, I'm sure. I'm looking very much forward to that. If you have feedback, as always, about how we can do this better, in general or specifically about the Rump session, also from the speaker's side, would be very happy to hear either in the chat or you send us an email or whatever, how it went. And then thank you very much. And we leave it on for 5 minutes or something like this. And then I see you all next week. Bye-bye. Thank you.